I did my test.
You have like a box or
Okay. Let's get started. Excitement. Where we were working on this problem last time when time expired. And there's a secret to help you out, which we didn't talk about. So I wanted to talk about this secret today. So this was our basic setup where we have an R1 and an R2. So basically this is the vector from A to B, and it's given in terms of its y component and its x component. And then R4 is theta 2 and theta, or actually theta. And what was theta? That was 60 degrees. So that makes life easy. This is the funny one where R1 was 2.5 inches and R2 is 6 inches. And so your angle here, phi, is just ugly. So our basic equation is the acceleration of A, B, C, D, D. Now the acceleration of C is equal to the acceleration of B plus the acceleration of C with respect to B. Acceleration of C is on link DC, and so therefore whenever we have a link, something on a link, we're going to have a normal and tangential component. BC is also a rigid body, so it's going to have a normal and tangential component. Or actually, B is on a rigid body between A and B, and so it has a normal and tangential component. And lastly, BC is on a rigid body, so it's going to have a normal and tangential relative component. This is the acceleration of B with respect to the ground. A and A doesn't move, and so the absolute acceleration of B is the relative acceleration of B with respect to A. Acceleration of C, well, since this is actually acceleration of C with respect to D, and D is on the ground, and so that the absolute acceleration of C is actually the acceleration of C with respect to D. Normal and tangential component. The normal component is what? It's r omega squared, which in our case, since we're at rest, all of the accelerations normal are going to be 0, since omega equals 0. So we basically have an acceleration of C, acceleration of B, acceleration of C with respect to acceleration of C, acceleration of B plus acceleration of C with respect to B. Acceleration of C was going to be R4 times alpha CD, and we said that that was going to be going what? Your R alpha is always perpendicular to R, and so that's going to be going up like this, assuming alpha CD is like that. And so that's going to be going up to the right. And if this is 60, yeah, so this will be 60 degrees like that. Equals alpha BA. Well, now we have these funny angles. But what do we really care about?
The length.
The length, and what do we care about? What's the next thing we do?
What?
In the x direction, right? The next thing we're going to do is break it down into components, right?
Break them down.
So we can break it down right now. How do we get an x component of acceleration of this? How do we get a horizontal acceleration?
That's not my R1.
We need the vertical distance. And how do we get a vertical acceleration? We went by the horizontal distance. And so we can actually break it down here. We can break this down into R2 times alpha AB. And that's going to be, is going to be, what direction? Well, do we have an alpha given? We just have an alpha, which we don't know what it means. We have direction? Yeah. The door. And so basically we assume that this is alpha AB. And so therefore R2 alpha, what direction is that going to be? Up or down? going to be down. As the door is rotating around like this, accelerating, the acceleration based on R2 is going to be down. And then we're also going to have an R1 alpha AB. In what direction is that going to be? So it's either the left or right. It'll be, as we're rotating around like this, it is going to be to the right. That direction. I can't remember my left and right. Right, so as this is accelerating counterclockwise, this point is going to be going to the right, this point is going to be going down. And so this combined is AB, the absolute with respect to A, tangential. What if we had a normal? We would have R2 omega squared this way and an R1 omega squared up. So whenever you have something complicated like this, it's easier to break it down into its x. Since you're given the x and y components of your vector, it's better to keep it that rather than to try to calculate the total length and then take the sine and the cosine. Because what you'd end up with is these two terms right here. So that's a shortcut. If you're given an x and y component of your radius, then you can go directly to your x and y component of your tangential and normal.
Is there not a normal? Why'd you cross off normal?
Because omega is equal to 0. We're starting from rest.
Okay.
So therefore, the velocity analysis, if this point isn't moving, then this is the structure, and it doesn't move either.
Right.
So that was from last class, and that's been 2 days. And I reviewed this before I came in, but you didn't. So that is a very good question. So we basically have omega is equal to 0. We're starting from rest. If we weren't starting from rest, life would be a lot harder. And then we would have this equation, but this equation would be for omega. We first have to solve this equation for omega. And then based on omega, then we would have, this would explode. And we don't want it to explode. So that's this. What about this term? So plus R3 times alpha BC, and this is in what direction? This is also to the right. And so this term here is that term there. And then we can break, once we have it like this, then it's a lot easier than trying to figure out what R1 squared plus R2 squared, the square root is times alpha, and then breaking down the sine and cosine. So then we can basically take our equations in the x and the equations in the y and go from there. So I wanted to basically do this because this is a lot harder than what we're doing here in today's lecture, which is, what is today's lecture? No, moment of inertia. This is the end of kinematics. Next up is kinetics. So now we have F is equal to ma as our fundamental equation. Now we're going to look at what happens when we're rotating. We have the sum of the moments now that we can rotate, and that's equal to I alpha. But we're just trying to figure out what I is today. Based on I, now once we figure out what I is, then we can go from there. So, any questions on the homework? I forgot to ask. It's a Monday question. So, we're going to look at a reading quiz, look at some applications, and then look basically how to calculate the mass moment of inertia, which is a calculus term, and then parallel axis theorem. If you have several different bodies, you can combine them without doing a lot of calculus. Let someone else do the calculus for you. Basically to get composite bodies. So we should be able to calculate the moment of inertia of the rigid body by the time we're done today, and that's using calculus, assuming you can do calculus. And then you can express the moment of inertia as a radius of gyration, which in Egypt they call gyration because they don't have a J. So they have other letters we don't have, but they don't have a J. I haven't started the clicker, and therefore, started. All right, now you can successfully choose BB. Don't forget. All right, 22, I think is how many we have now. So what's the answer? C, angular acceleration. I even said that at the beginning of class. So if you were paying attention and knew what I was talking about, then so some of the moments is equal to I alpha, so that alpha is your angular acceleration. What's true about the mass moment of inertia? It's always seconds total. Oh, I'm sorry. There's 3 people. Someone got cut out last time. Okay, it's always positive. It's just like math. You can't have a negative math. No. So, flywheel. A flywheel is designed such that it has a large amount of radius of gyration, or the large I. What do you want a flywheel to do? Why do you use a flywheel? You want it to keep moving, and so you store energy, and so we want to figure out, well, what is I going to be? Why is most of the mass located near the outside edge? So that is a larger moment of inertia. It's your mass times your distance squared, so we want to put our mass out as far as possible for low-speed flywheels. Here we have a crank as we're rotating, and so this is going to be rotating, causing this to go up and down. And what's the advantage of this going up and down?
Oil.
And when it goes up, it's taking oil up out of the ground, and that allows us to drive our cars and have plastic and stuff like that. But basically, you need to know when you're calculating how big a motor you're going to need, you need to know the mass moment of inertia. You're also going to have what? Now we have a link A, B, C, D. So to solve this problem, you need to do what? Your kinematics. And so this would be the starting type problem, how to start to solve this problem right there. Or you'd probably use a computer to do the solve. So we have a rigid body. Center of mass is at G. And we're trying to figure out, it's free to rotate about the z-axis. How hard is it going to be to rotate? So if we apply a torque, we want to spin this like a top. We're going to rotate with an angular acceleration of alpha. What is mass? What is mass? How do we figure out what a mass?
Weigh it.
Well, you can weigh it. How would it in space? How would you figure out what a mass is? You apply a force and you measure the acceleration. And the ratio of force to acceleration is fairly constant, and we call that ratio the mass. Similarly, rather than linearly accelerating, now we're trying to spin it. We're trying to give it a rotational acceleration. We apply a torque, we measure the rotational acceleration, and the ratio of the torque to the angular acceleration is this moment of inertia that we're trying to find. It's a mass moment of inertia. So by torque is equal to I alpha, I is equal to the torque we apply divided by the alpha we get. And that's the mass moment of inertia about the z-axis. The property of the body, so it's resistance of the body to angular acceleration, just like the mass is the resistance of the body to linear acceleration. So basically we have dm, which is in general, and it's at a distance r. So as r increases, how does that relate to how hard it is to accelerate? It increases, right? You put your hands like this, or you put your hands like this. It's harder to turn when you're big. When the mass is further away, it's harder to turn. And it turns out that it's proportional to the distance squared, not just the distance. And so how hard it is to turn this little mass? It's the mass times r squared. So how would we find if we add up all the little masses? How would we add up all the little masses?
Integral.
We take the integral. So we do the surface integral of the entire element. And so angular momentum, r cross mb. So it's r cross dm omega cross r, or dm r squared omega. The velocity is r omega. And so that's how we get the r squared. It's in kg meters per meter squared. Since it's meters squared, it's always going to be positive. Or slug feet squared, which we don't like those. But that's what it is. So we can do the calculus, and for a thin cylindrical disk, we have Ixx equals Iiy equals 1/4 mr squared. Izz is equal to 1/2 mr squared. What does Izz mean? Oh, I don't have a big circle. Right? So here's our disk. Izz is if we're rotating about like this. Rotating about like how we think a yo-yo should rotate. That would be Izz, rotating about an axis here. What is Ixx? Now we're rotating our yo-yo like this. That would be Ixx. So Izz spins this way, Ixx spins this way. And so if we're rotating about the x-axis, we're flipping a coin. Rotating about the y-axis, we're also flipping a coin. And that's equally as easy to flip a coin in either direction because it's symmetry. But to spin a coin, it's harder to spin a coin. So that's 1/2 mr squared. And this is like for a wheel, we would typically have a disk that's 1/2 mr squared. I z prime z prime. What are we doing now? We're rotating about our coin about the end, not about the middle.
And that should be the hardest, huh?
And that's harder because you have more mass further away. And so that's 3/2 rather than 1/2 mr squared. So this is useful in sometimes we're rotating. When do we rotate a coin about the bottom?
On a wheel.
Yeah, a wheel rolling. Typically we would need Izz in terms of energy. That's very helpful. So these are pre-calculated for you, so you don't have to do the calculus and add everything up. So these are used as differential elements. So direct integration. We have a shell element, so this is our surface we're trying to do the integral of. This is our shell integral, so we basically have a little dx, and then we have a height. So it's mass times radius squared is the integral. So what is I for this? It's the mass of the shell, and since this is a little dx, all the mass is located at the same distance away. So I for this is mass times radius squared. So if we had the density, we would have to calculate the volume. But basically for a shell, the I is the mass times the radius squared. If we had a disk element, what's the I for a disk? 1/2 mr squared. So it's the mass of the disk, and then if it's divided by 1/2, because not all the mass is located at the outside of the disk element. So depending on what we have, it might be easier to use shells, or it might be easier to use disks. Let's do an example. You know the volume shown with rho equals Lecture 5 slug per feet squared, because we all love slugs and feet. So we know a density. It would be kilograms per meter squared if this were meters cubed. We want to find the mass moment of inertia of our fine body right there. So we know x and y, and we have the bounding curve is what?
Is it solid?
It's solid, yes.
Okay. Access to the middle, let's see.
So the middle sort of looks like, so basically the bounding curve looks like this and like this, because it's symmetric. So basically we have y squared equals x. And then it's going to be flat across the top, and this is 1 foot, and this is also 1 foot. And so this is actually, let's use a different color. And so the top of this is basically a circle. Now let's first try using disks, because that's the easier way to do it in this case. So let's set up a disk at an arbitrary height. So here we have our disk. This distance here is dy, because we're going to be integrating our disks going upwards. So what do we know? We know that I disk is equal to what? 1/2 mass times radius squared. So therefore we're doing this about the y-axis. We're rotating it this way. We're not trying to spin it around the x-axis. So Iy equals, well, what do we need to integrate from? Integral from 0 to 1. We need to integrate over the entire distance. So this is 0 to 1 feet of what? Mass. What's our mass going to be?
Rho.
Rho.
Times
So this is your density times the volume. What's the volume going to be?
pi r squared.
Pi r. What's the radius going to be?
X.
X.
Dy.
Pi r squared.
Dy.
Pi r round. Cornbread r squared. The pi r. So this is pi. This is your radius is x times squared times the height, which is dy.
Times
So this is the mass times your radius. What is your radius?
r squared. X squared.
X squared.
Over 2.
And then we need it, yeah. So the x is your r squared, and then this term here is your mass, and then we need a half. Now we're integrating into y, but now we have x in there, and so what do we need to do?
Substitute.
Substitute, right? We have the relationship between x and y squared. So this is equal to the integral from 0 to 1 foot of rho pi. So we have x to the 4th, but x is equal to y squared. So it's equal to y squared to the 4th.
Yeah.
Right? We have x squared here times x squared here. That's x to the 4th.
Over 2.
Over 2. And then we have our dy coming out. So this is equal to what? Rho pi over 2. Integral of y to the 8th. Y to the 9th over 9. Evaluated between 0 and 1. So that's equal to pi times 5 slugs per feet cubed. 5 pi rho. And then y is 1 foot to the 9th over 9. And this is over 2. And so this, when we end up doing the calculations, this is 0.873 slugs feet squared. So that's IY. What if we wanted to do this using disks? Using rings. What's the ring going to look like? If you like it, then you better do it.
doing like this touch. I don't touch this and then show me it's like
I can't. I didn't get those genes. So there is our ring element. Right? This is a ring here, hollow. And so what are we given? We have I, Y, ring is equal to what? M times R squared. So for our case, what is mass going to be? So this is y squared equals x. These are our curve. So what's the mass going to be?
2 pi r.
So it's 2 pi
Rho 2 pi
r. So it's your density times 2 pi. The radius, what's the radius? X. So that would be your perimeter times
y.
dx.
Yes.
Your thickness, that gives you the approximate the area of the top ring, and then times the depth, which is,
Y.
no,
1 minus 1.
it's 1 minus 1. So the ring goes from 1 down to y. So this here is your mass times your radius x
I don't like this.
squared. Okay, now we gotta get rid of that y. Oh, we need to integrate this, and this from 0 to 1 flips. Again, now we're integrating this way, where before we integrated that way.
And don't need to multiply by 2, is that included?
Why do we need to multiply by 2?
Sides?
Why do we? It's just mr squared. This is m times r squared. But now we need to substitute. Now it's dx, so we need to write y in terms of x. So we get y equals square root of x, and so now we have to integral from 0 to 1 of rho 2 pi x times x squared, so it's x cubed, times 1 minus square root of x dx, moving this out to the end. And that says for stat. Right, because I can't do that. This one was easy, I can do that one. And so depending on what your function is, how x and y are related, sometimes it's easier to integrate in the y direction, and sometimes it's easier to integrate in the x direction.
Here, x and x cubed should be just x cubed.
But, so if you're integrating from 0 to 1 on the x-axis,
Mhm.
don't you need to multiply it by 2 or go from -1 to 1?
No?
No?
Because we have this, the rings start here and go there. Because here it's the same ring as here, so then you'll be
Yeah.
doubling it.
Yeah.
So your ring size starts at 0, and then the rings get bigger and bigger and bigger until we get to the top. So it's still the same range of integration. The fact is here we have hard calculus, and here we would have easy calculus. Question?
Yeah, at the bottom, the units are slug feet squared.
It should be, so
Or
something.
slug over feet squared.
It should be slug over feet. Start to say, and the bottom, what?
The answering.
It should be slug. No, it should be slug feet squared. Yeah, slug times.
And feet to the,
Well, no, if you look at mr squared is slugs times distance squared. So
Yeah.
it should be
so
slug feet
when everything
squared.
worked out, so somehow I lost a unit. How did that work?
Integral.
D. Oh, this is a problem. This is where our problem. This is where the units got missed. Right? Because this, what are the units on this?
Feet.
So x is in feet and y squared is in feet squared, so we're missing a what? So this is y squared over feet. Right? So this is y squared over feet for our unit. And so what this ends up with is what? Y to the fourth, or feet to the fourth. So then this would be, here we would have, down here we would have feet. Feet to the fourth down here. And so the feet to the fourth divided feet to the, so it's feet to the ninth over feet to the seventh, which is feet squared. So thank you. But there's the mysterious sign conversion, which we didn't take into account. But units are important, and units tell you when you got lost usually. And so that was magic. Use your hands and it all works out. All right, since we got a little late start, since I went over this, I'm going to skip the next example, but we're going to talk about parallel axis theorem. So, how do you combine things? Rather than having to do the calculus every time, we can actually use the parallel axis theorem to do a composite moment of inertia. And so what happens? We can figure out how hard this body is to rotate it about its center. How hard is it to rotate it about A? How much harder? And it turns out, if you do all the calculus, it's how hard it is to rotate it about its center plus mass, the total mass of everything, times the distance squared. The distance is the distance from A to the center of gravity. This is the parallel axis theorem. And so if someone has already done the calculus for this, if this is a disk or this is a sphere or a rectangle or a cube or a thin rod, if we're rotating about this, we can let someone else do the hard calculus for us and just use the parallel axis for us. And so it's a perpendicular distance between the parallel axis, the distance from the center of gravity. So radius of gyration is sort of a corollary. So for an object, we can have I, which is the radius of gyration. What is that? It's the mass of the object times k, which is your radius of gyration squared. So what is this saying? What did it say? Here's an object. We want to rotate our object about its center. So how do we figure out the mass moment of inertia? We have to add up all of the little masses times their distance to the center squared. That's how we do it by calculus. And what does this say? That what we can do is replace this object with an object with the same mass at a distance k from its center. So put all of the mass in the object at a distance k, it'll be just as hard to rotate. Conceptually the same. That it's just as hard to rotate with all the mass distributed as it is, or if you put all of your mass at a distance k, the radius of gyration squared from the origin. So it's parallel axis. If you have a single point, it's how hard is it to rotate? Very easy. It's 0 because there's no distance. And so the parallel axis says if you put all your mass at a certain distance, it's just as hard to rotate. So this is the terminology people use, and so you can either give it, on the test I can give you I, or I can give you K. And if I give you K, you say, no, it's not that hard. You just square it and multiply it by mass, and there you get your I. So composite bodies. What happens if we had two things stuck together? We basically add them using the parallel axis theorem. So found about the same axis, different shapes. So here's the example we're not going to do because we'll do the same type of stuff in the next one. You have have your book with you?
No.
I think it's way
No.
too heavy.
It's too heavy. It's too large of a mass. Do we care about the mass
Moment of
moment of
inertia is
inertia?
gigantic.
Yeah, you have 2 books rather than 1 book. Okay, so you can't use your book. So moment of inertia, rod mass, L about its end, it's actually 1/3 ml squared. So C is the right answer here.
What's the 12? Is it?
The 12th is about its center.
Oh,
1/3 is about its end.
Oh.
Because 1/12 plus 1/2 squared, or 1/4, is equal to 1/3. All right. Mass moment inertia about a thin ring of mass m and radius r about the z-axis is what? This one you don't need your book. How hard would it be to rotate a thin ring with mass m and r, radius r? There we go. So what is it? It's the integral of the mass times the distance squared. What's the distance?
R.
Since it's a ring, everything is distance r, and so it's mr squared. Which is b. Right? It's right here. I ring equals mr squared. Immediately. Okay, now we have a pendulum. And it consists of 5 kg plate and a 3 kg slender rod. We want to find the radius of gyration of the pendulum about an axis perpendicular to the screen and passing through its center point G.
Whoa. About G?
About G, not about O.
Oh.
No, G.
Oh.
Not O.
Oh.
So, first thing we need to do is figure out where G is.
Right there.
It's right there.
Wait.
So, how do we figure out what G is?
Rig gyration of the whole thing is back to us.
The parallel axis. So basically what we can get is y bar, the distance to the center of gravity, is equal to the sum of the y times m over the sum of the m. So the center of gravity is the sum of the distance yi times mi over the sum of mi. So this is I. Right, so we add up all of our masses. It's a weighted average of the masses times their distance over all of the masses. This goes from, did you do this in statics? Yes. Wonderful. So you all can do this. And so in our case, what is it? It's a 3 kg rod. What's the distance to the center of the 3 kg rod? 1 meter is half of 2, plus we have a 5 kg rectangle thingy-dooey. What is it, plate? Times, what is its distance?
2.25.
It's 1.25 meters, and we need to divide all of this by what? It's what? Oh, 2 point? It's 2.25. It's 2 for the rod plus another half to get to the center of the plate. Thank you. And this is over 3 kg plus 5 kg, the sum of the masses. And we do this. This is some nice number, 1.781 meters.
say that that was the parallel axis here?
No.
Okay.
People were saying we should use the parallel axis theorem, but no, this is just it's the center of mass theorem. The center of mass equation. Right? It's a weighted average of the mass times the distance. That's basically what it is. So now we know the distance, 1.781 meters, give or take 0.001 meters, to the center of mass. So now we need to figure out what IG is. Well, now we have two components, right? What is our plan? Well, we want to figure out, use our table to figure out the mass moment. We're going to use the parallel axis. So, IG, what's IG? Well, now we have two components. We have a rod. And for a rod, what do we have? It's 1/12 mass of the rod times L of the rod squared. As you get from the front or back of the book, there's a table which has these in it. So this is about its center of gravity plus, what do we need? The parallel, now we're using the parallel axis theorem. So it's the mass of the rod times what? Some distance squared. What is that distance? Well, the center of gravity is at 1. And so we need the distance between 1 and the composite center of gravity.
0.78.
And so that's going to be 1.781 meters minus 1 meter. Here's my beautiful drawing. Right? So here's the center of gravity at 1.781. This is 1 meter, and so we need this distance here is the distance between this mass of the rod. This is the center of mass of the rod, and this would be mass of the plate. Okay, so now we have the mass of the rod squared.
So now do we do the same thing for the block?
And then plus the mass of the plate. And for a rectangle, that's 1/12 mass times base squared plus height squared.
This is about the center of the.
This is about the center of gravity. So then we have plus mass of the plate times what? It's 2.25 meters minus 1.781 meter squared. How are these related? These two terms right here. A plate and a rod. How could you get this from this? They're both rectangles, but this is a rectangle where what?
There's no base.
The base is small.
Negligible.
Negative. So it's if the base is 0.1 and this is 2, then 0.1 squared is 0.01 plus 2 squared is 4, so it's 4.01 compared to 4. So the real answer is 4.01, but we're really not quite sure about the 4 that closely. And so that's why if this is much skinnier than this, then we can just use 1/2 mr squared. This formula always works. It's just, this is easier.
The other one's kind of almost approximation.
It's an approximation. Because we're not actually at the right answer, we're actually close answer. Right? We're neglecting air resistance all the time, which is going to give us the wrong. And the manufacturing tolerances. So we're just trying to get close. All right. So if we plug in our numbers, this is 1/12. Mass of the rod was 3 kg. Well, we'll not plug in numbers. I'm assuming you can plug in what we get. I'm assuming you can plug in the numbers.
Yeah.
And this is 4.45 kg meters squared. So we're almost there. What is K? Well, we know that mk squared equals I, so therefore K equals I over m to the square root. It's equal to I was 4.45 kg meters squared. Divide this by 8 kg, take the square root, and that's 0.746 meters. And that works out, the kg cancels with kg, giving us meter squared square root meters. All right, let's see. You got time for this or no?
Yeah, it's already.
We're already out. Okay. Mass molar inertia of any body by the center of mass is always minimum. Because it's the center of gravity plus mr squared, and so going minimum about its center. And if Ka is 2 kb, then Ia equals 4IB, because it's mk squared. So C is the right answer. That's it?
Okay, got it.
Just one last time.
Hey, do you want to talk
Can we do by the finger here? The word?
I was in jail at one point.
All right.
In jail at one point, but I just worked with it. I just had this out. We're all like in that with like all our hands on it. Blah, blah, blah. Anyway, so there's a girl. So we get into the free zone, and I like let her go, but she's like still holding on to this. Like my hand is like she's still holding like the next like 3 seconds on the free zone. I'm just like trying
Maybe
to
it won't
pull
be
it,
good.
she's still holding on. She's like,
Yeah. I figured it'd be more this. Well, I don't know.
I don't know you.
Well, I'm gonna get fired. I figured like more people would do
anyways, it was kind of
Well, yeah, I guess.
That was fun. It was. And she was even more fun because
It's go.
I was talking with Chris.
It'll work out.
No, I was talking with
Theta B was not 0. Theta B was 0. Theta B was 0.
like, I want to hold yours.
Sure?
Symmetric.
What do you get for your Theta A? Huh? What do you get for your Theta A? 360? I don't remember. Theta A was like.
They're wide, but
I as long as I can have like a week where I don't do homework, do you want stuff I'm not being written in, you know what I'm saying? Then I can
They're flat. They're flat though.
Oh, you're already there. Oh, confusing people.
It's better to just go to homework than to
But yeah.
previous exams. Yeah, 3 out of 4
3 out of 4
problems.
are 2 out of 3 problems.
Oh, 3?
What? Probably.
That's what you say?
Probably. I mean, depending on.
Make it a yes.
Right. The problems have gotten more complicated.
Yeah, I know.
Right. We used to have, x is equal to x0 plus v0t plus 1/2 at
He's gonna have
squared.
one where it's like got energy,
Now we
momentum,
have-
impulse, everything all in one. Watch.
Well, we went from, that equation to this.
That's confusing.
That's
gotta
only
get-
that's what I'm
gotta-
struggling with right now is the acceleration stuff.
Yeah,
Rotating.
it's the hardest part.
It's very.
No, see, velocity, I'm cool. I got it.
Yeah, it's basically accounting, keeping track of normal and tangential,
Dude, direction and
Okay.
oh my goodness.
and directions.
All right, I'll see you guys on Monday.
Bye. That's good.
You were supposed to take pictures.
I was supposed to take pictures.
It's still recording.
Still recording. So we have the shoes in there.
It wasn't me.
That was me.